So, good morning and welcome to today's lecture. So, this is the 19th lecture. So, today we will have some recitation topics. So, we will revisit some of the topics that we have discussed already. So, that would be helpful for your internal test in the month of November, also for your final exam. So the first topic here is the binary eraser channel. So we have seen this. So in case of binary eraser channel, we have the binary inputs 0 or 1, and we expect those outputs 0 or 1 at the output point y. But it is possible that when the data is transmitted from the source to the destination through the channel, it may flip here when it travels from the source to the destination, and you may get something, the receiver may get something that is unpredictable. So we have a question mark here. In that case, how the receiver can send the feedback and get the data corrected through retransmissions from the source? That's the binary eraser channel. So here it's a symmetric channel, because if the bit 1 is transmitted, it may appear at the receiver with probability PE as some unpredictable one, or in the remaining probability, that is 1 minus PE, that will be supporting the transmission of 1 and reception as 1 itself. That means 1 minus PE is the probability for right transmission, and PE is a probability where the data gets something else unpredictable. So it's still a symmetric channel. So in this case, so we have seen the definition of binary symmetric channel. We have the binary data, and at the receiver, again, we will be expecting the binary output, but it's possible that we may expect something else, or we may get something else which the receiver cannot predict. In that case, the receiver has to send the feedback to the channel, to the sender transmitter, and the transmitter will retransmit until the receiver can properly decode the information. So we need a feedback channel in this case, in addition to the data channel. And also we seen that it's a symmetric channel because we have the probability of alpha or 1 minus alpha, where 1 will be leading us to the right transmission without any error, in the other case leading to an ambiguous transmission. Okay, in this case, how to determine the channel capacity? So channel capacity is given by the equation CS is equal to maximum of the mutual information between X and Y. So we have multiple contenders based on the input what you transmit and output what you receive. So out of those multiple informations, IXY, so one that gives a maximum will be the channel capacity. Now we will see one example here for this concept. So what is given? A channel is given here. Here we have 0 and 1, and at the output we have 3 points, maybe 0, 1, or some unknown term E. So from this channel diagram, you need to find out the information XYJ for some specific cases. For example, information 0, 0, that means you are sending a 0 here and you're receiving a 0 here. Then what's the amount of information you convey here? Mutual information. And the case 1, 1, so you send a 1 here and receive a 1, that is x2 y3, and then 0e. So you'll be sending a 0, but at the receiver you expect some other things e. So x1 y2 is the combination that gives us this particular information. And also one more information is given, that is probability of the inputs. Probability of x1 and probability of x2 are equal, that is equal to 0.5. So with this information, how to determine these parameters? That's the question. So first, when we see the channel conditions, the probabilities, we can easily write the channel matrix. That's the conditional probability of the output when we know the probabilities of the inputs here. So that is simply a matrix that is we have the x1, x2 as the row items, and along the column we have y1, y2 and y3 here. So x1 to y1 is 1 minus p, x1 to y2 is p, x1 to y3 there is nothing. That's why we have 1 minus p, and nothing, 0 here. Similarly, this second row corresponds to the data transmission from x2 to different output points y1, y2 and y3. Okay, when we have this information in hand, we can do some more things. For example, we can find py is equal to probability of x multiplied by the conditional probability. We know this parameter. So with the help of that, we can try to find some unknowns in this equation. We already know here in this equation, we already know p of x. P of x is a probability of the input, probability of the x1 and probability of x2. That's given in the question. So with that, probability of yx, I mean, since we know probability of yx and probability of x, then we do this computation here. That's basically multiplying the two matrices. This we have found in the first step, and this is the input given. So we just multiply those parameters to arrive at this value. So you multiply this and this metric, then you'll be getting p of y. So that's what we wanted here. So P of y has three elements in the matrix as seen before here. So this represents this P of y. So here we have py1, py2 and py3. These are the probability of three different output points y1, y2 and y3. So that's what written here. Probability of y1 is this, probability of y2 is this, and probability of y3 is this. Now we find the joint probability between x and y. So we know the joint probability is equal to the diagonal matrix of the input multiplied by the channel matrix, that is yx. So we know the diagonal matrix, and along the diagonal we have the probability of the inputs, that is px1, px2 in this case, and remaining elements will be 0. And we know this matrix, that is the channel matrix, we have already found in the first step. So we just need to multiply these parameters to get pxy. That's the joint probability between x and y. Now, after the multiplication, we should be landing at this matrix. That is, basically we multiplied this matrix and this matrix, and then we get pxy. That is what shown here. We get pxy. Okay, then moving further, now we have this relation, that is the channel matrix is equal to the joint matrix divided by p of y. We already know p of y, and we know this here in this step. Now we can find out the conditional probability of the input, that is pxy. So that is by dividing this matrix by the elements of the column p of y. So that is something like this. The first element 0.5 multiply 1 minus p is divided by the first element of p of y matrix, because p of y has three items, py1, py2 and py3. So we divide py1 here and also py1 here. I mean, this element is divided by py1. So in general, this particular column is multiplied by probability of y1. This particular column elements are multiplied by probability of y2, and this particular column here is multiplied by the probability of y3. This is this py matrix we have already found. If you want, I just go back to show you py. So py is here, the different elements py. The different elements are py1, py2, and py3. This is a row matrix. Okay, that we have used here to divide this matrix by py1, py2, and py3. So when we divide that, we will be getting the term pxy, that is the conditional probability of the input. So the value is something like this after the division, and then we find the first part, that is the information between input and output, mutual information. So mutual information is given by this equation. This is a well-known equation, that is entropy of the input minus the conditional entropy, the input. But we don't need the entire matrix, but we need some specific cases from this matrix, right? There are three questions asked in the, in the main question. So we will use this general equation to find out the specific elements here. For example, mutual information between this xi and yj. Not every element of x and y. We need only some specific elements. That's equal to the specific element xi, its information content, minus the information content of xi and yj. It's a conditional. So that is nothing but log of 1 by probability minus log of 1 by probability. So here information content is log of 1 by probability. This is the equation we have visited several times. So that is what applied in the next step. Ix information is nothing but log of probability 1 by probability, and the second term log of 1 by probability. Okay, here we can simplify this log subtraction, log a minus log b, that is log of a by b. Since it is inverses here, 1 by px, 1 by px I yj, it also gets inversed, that is log of b by a. That this term comes to the numerator and this term goes to the denominator, and so on. Okay, with this we will find out the exact terms that we need. Information of 0 and 0, that is xi and yj. Your input is 0 and you are getting the output also 0. Then what is a specific case? Xi, x1, y1, right? This is from the diagram that is given in the question. So we use this direct equation to substitute the values here. That is probability of x1 y1 divided by probability of x1. So this is the general equation that we arrived here through these steps. Now we will be interested in some specific cases of xi and yj. In this case it is x1 y1, so we have substituted those values here. So if you observe the panel diagram, then you can easily write that the values becomes log of 1 by 0.5, because the probability here is this much and probability of x1 input, that is equal to 0.5. So we get the value as 1 bit. That's the amount of information. So if you want to check this, you just check these two matrices, that is pxy. This item is picked from this particular matrix that we have already found in the previous step, and this value is picked from the input, that is px1. So this is the input given, input information, and this we have found already in the previous step. So one of the element from this is px1 y1. That's the first element in the matrix. If you want, I can go back to show you p here, first item. for xy. Okay, pxy, the matrix pxy is the yeah. Okay, so now let us move on to the next items that we want to find. So I11, we need to find out the next values for information for 1 case, that is input is 1, output is also 1. When do we get it? When x2 is 1 and y3 is 1. This case corresponds to these input output combination. So then we use the same equation here, px2 y3 divided by px2. So again the values are same, I mean picked from the same matrix probabilities. Finally we have this case here, information of 0 and e, that is I x1 y2. So that is again we substitute the values for x1 y2 divided by probability of x1. So we get 0.5 and 0.5, that gives us 0. Okay, now we will see the other case, that is regarding the mutual information. So we have a specific example here. So a channel is given here, two inputs x1 and x2, and we have three outputs y1, y2 and y3. So in this case, first we need to find the rate of information transmission over the channel, and it is given that the probability of inputs, it's x1 and x2, are 0.5 and the rate is 1000 symbols per second. So the rate of information transmission we need to find, that's the main question. So we have some well-known equation to find this, that is the mutual information between x and y. So mutual information between x and y can be found in two ways. One is, that's the entropy of the output minus the conditional entropy of the output, or because it's also equal to entropy of the input minus the conditional entropy of the input. But we may use this equation or this equation, but if you see the first equation here, that is much more easier because we have the channel here. With the help of channel we can write the channel matrix, that is pyx. With the help of pyx we can find hyx, because once you know pyx, then hyx is nothing, is the entropy, that is pi log pi, that equation or that relation you need to use. So that is easier, so we will use this equation. However, this equation can also be used, but maybe it requires more steps, we need to arrive at these terms. Okay, now we will choose this equation to find the mutual information between x and y. So from the given channel we can easily write the channel matrix pyx, that's equal to x1 y1, which is 3.3 by 4. Next x1 y2 is 1 by 4 here, and x1 y3, that is nothing, 0 here. Similarly for x2 we can write the values here. Okay, with that we will proceed, that is we can also find the joint probability matrix, that is pxy. Pxy is pyx, that is the channel matrix multiplied by the probability of the input. So we have found this term, and we also know this because these are the probability of the inputs, probability of x1, probability of x2. It is given in the question that they are equal, 0.5 and 0.5. So to find this, the joint probability matrix, it's very simple, you just need to multiply these two matrices. We know those values, so we just need to multiply this matrix and this particular matrix. So we know pyx is here. We have to multiply this matrix by 0.5, 0.5. I mean this matrix. So that should give us these values. That is the JPM, joint probability matrix. Now from the joint probability matrix, that is Pxy, we can write P of y. That is the probability of this y. That is nothing but we just need to add these terms along the column. So that is 3 by 8. Here it becomes again 3 by 8 and this becomes 1 by 4. So that gives us Py, probability of the output. Now from the probability of output, we can easily find the entropy using the well-known equation of the entropy. Entropy is equal to minus probability log of probability. So that we do here. We know P of y. So for every element of P of y, that is 3 by 8, 3 by 8 and 1 by 4, we find this and finally we get the entropy. So entropy should be around 1.61 bits per 1.561 bit per symbol. And then we find another term, that is the conditional entropy of the output. Again, we have the same relation, that is probability Px xiyj log of conditional probability. So this is the well-known equation to find the conditional entropy of the output. That is nothing but the joint probability matrix multiplied by the conditional probability matrix of the output. Now here, these terms Pxiyj are taken from this particular matrix, so this matrix, Pxy matrix, and these terms are taken from this particular matrix. So we have 3 by 8 log 3 by 4 plus 1 by 8 log 1 by 4. If you want, I can show you these values. That is, since we need to find out these values comes from these matrices. I mean each element of this and each element of this, that we will be substituting here. For example, when we have Pyj we need to refer to this matrix. Each element of this matrix we will be considering here to substitute. That's 1 by 2, 1 by 2, 1 by 4 and 1 by 8. And when we have P xy, that is the joint probability matrix, that is taken, I mean these values are taken from this matrix, each element. So they are 3 by 8, 1 by 8, 1 by 4 and 1 by 4. So we will see that. Go back and see Pxy, are they corresponding to 3 by 8, 1 by 8, 1 by 4 and 1 by 4. So Pxy is here, Pxy matrix. So they are 3 by 8, 1 by 8, 1 by 4 and 1 by 4. Other elements are 0, so that's not considered. And another term what we need here to substitute is Pyx. So this is the input matrix, right? So input matrix elements are, I mean they are taken here, so that are nothing but 3 by 4, 1 by 4, 1 by 2 and 1 by 2. So we will go back and check this matrix Pyx, because we will be substituting Pyx. Yes, Pyx, they are 3 by 4, 1 by 4, 1 by 2 and 1 by 2. That is being substituted there. Yes, so those values are substituted and we get the, I mean when we compute we get those values. So Hyx, that is what we have computed here, that should lead us to 0.9056. And then finally we need to find the mutual information. So mutual information is given by this equation. This is what we have seen initially. To find out this term as well as this term, to substitute here, we did all these steps. Okay, so since we know these values, hy we have already found and hyx recently found, so the difference gives us the mutual information. And now the rate of information is given by the well-known equation, that is, it's the product of the mutual information multiplied by the rate of information arrival. So that is, this is given in the question that the system or the channel accepts 1000 bits per second. So when we multiply, we should be getting this value. So many bits per second is the rate of information. And then we will move on to mutual information again. So in this case, we will find out the different ways of finding the mutual information. So basically, we will be revisiting the different parameters, I mean different properties of mutual information. We have three properties of mutual information that we already discussed. And how do we use those properties and how can we verify them? That is what being addressed here. So I have a star mark here that indicates mainly we will be seeing the mutual information by considering the properties of mutual information. How can we represent the mutual information with the help of those properties, and how can we verify that? That is being the discussion here. So here we have some well-known equations. That's a mutual information IXY is equal to the entropy minus XYZ XY. That's the conditional entropy, or the entropy of output minus the conditional entropy here. The average rate of information transmitted by the channel is given by the mutual information multiplied by the rate. So when we substitute IXY from here, it could be HX minus HXY or this term. That is what shown here. So R is equal to mutual information multiplied by the rate of arrival of the information. Mutual information is given by either this equation or this equation. So that's what is substituted here as well as here. So basically this is the equation for mutual information and also the rate of information. Okay, we will see a specific case here. So we have a channel having two inputs x1 and x2 and two outputs y1 and y2, and the transition probabilities are given here. Also we have the probability of the inputs and the rate of information arrival is given here. So with this, what do we need to find? We need to find out the mutual information for three different relations. So we have a star mark here that indicates that we need to find the mutual information using the properties and find the rate of information transmission. So we know the equation for rate of information transmission. Now that is nothing but the mutual information multiplied by the rate of arrival of information. That's very simple. Once we find these values, then it just multiply that by r. That should give us the rate of information transmission. Now we will go to find out the mutual information for three different cases. So first of all, we need to find out the channel matrix, because we know the channel and its transition probabilities. So here h of x, so that is the channel matrix we will find here, and then we find the entropy of the input, because we know the probability of the input px1 is 0.6 and px2 is 0.4. So then we can find the entropy of the input. So that is equal to pxi log pxi. So when you substitute those values here, that is these values and this value px1 px2 here, and compute, then you should be getting this value 0.97 bits per symbol. That's the entropy. And now to find the entropy of the output, we will first define the probability of the output. That's equal to probability of the input multiplied by the conditional probability of the output. So this is basically the channel matrix. So we know these parameters. P of x we have already found in the previous step just before this, and then Pyx. This is in the first step we have found. We just need to multiply these two matrices to get P of y. So when we multiply this, we get this matrix. That is basically we get Py matrix having two elements Py1 and Py2. Those values are 0.56 and 0.44. These we get by the multiplication of these two matrices. So once we find Py, that is probability of y, then we can find the entropy of y. Entropy of y is nothing but probability log probability with a minus sign here. So we just substitute those values here and find the entropy of output y. So now to find the mutual entropies, we need to find the mutual probabilities. So from the joint probability matrix, we know that the mutual probabilities is equal to the product of diagonal matrix and the conditional probability, or the matrix, or the channel matrix Pyx. We know this matrix. Also we know these elements, that is along the diagonal we have px1 and px2, and remaining elements are 0. We just need to multiply these two to get the joint probability matrix, or the mutual probabilities between x and y. Now since we know pxy, we can easily find its entropy, that is probability log of probability of every element of these resultant matrix pxy. So that comes to be 0.48 log 0.48, 0.12, 0.08, and 0.32. They are the four elements of this particular matrix. Once we multiply these two matrices, we get those four elements, 2 cross 2. We substitute those values here. That is what we get here, 0.48, 0.12, 0.08, 0.32. So when you compute that, you get 1.6928 bits per symbol. Now we find the entropy, that is entropy of yx. So conditional entropy is nothing but px xi yj log conditional probabilities of the output. So now we have to refer to these two matrices. One is the channel matrix and pick up every element from the channel matrix, and JPM, joint probability matrix, and pick up every element from that and substitute here. So Pyx we already know, we have found in the, this is a channel matrix. The very first calculation what we do is finding the channel matrix, and then we have found the JPM in the previous step. That we will be those elements we will be using here. Pxiyj is this, and Pyjxi, these elements, corresponding elements we will be picking from this matrix as well as from this matrix. And when we compute that, we should be getting, when we substitute here pi log pi, those values from these two matrices, from the JPM as well as the channel matrix, we are substituting here, and we get hyx. That's equal to 0.7219 bits per symbol. And then we have hxy. We know that this is the joint entropy, that's equal to H, that's the conditional entropy, plus the output entropy. So now H, joint conditional entropy is equal to the joint entropy minus this. It's basically rearranging these terms, because this is the well-known equation, or the equation we know how to find the joint entropy. Since we know some of these terms, we just need to rearrange them. So this term is equal to this term minus this term. We know these values, so we can easily find this one as done here. Okay, with that we arrive at the main requirement, that is the mutual information between x and y. That's equal to h of x minus h xy. That's equal to 0.2671 bits per symbol. And then the second way of finding the mutual information, that's second property, hy minus hyx, that's equal to 0.2671. Now the third property is we can combine h of x, h of y, and substitute h xy, that's the mutual entropies. So that also gives us this value, because we know all these terms. So far we have found all these terms, we just need to substitute here and find out those values. So this is the way of representing the mutual information by three different ways. Now going to another case, that is the channel capacity. So a channel is described by the channel matrix, so that is defined here. A channel matrix is defined. Then how can we draw the channel diagram? So by seeing this question, you can realize that there are two inputs, x1, x2, and three outputs, y1, y2, and y3. So you need to connect x1 and x1, x2 with y1, y2, y3 based on these probability values. That's what is the first requirement in this question. Next, the probability of input and probability of x1 and x2 are given as 0.5. That is x1 and x2, that's the row elements. Their probabilities is 0.5. Now you find the probability of the output symbols. What's the probability of y, which consists of probability of y1, probability of y2, and probability of y3. And then specifically find some cases joint probability between x1 and y1, probability between x2, y1. These specific conditions you need to find. So how to do that? So from the channel matrix which is given, we can easily find write the channel x1, x2, y1, y2, y3, and x1 to y1 is 0.8, x1 to y2 is 0.2, and this is 0. That's what written here. That has been drawn here. And then we know this relation, probability of output is equal to probability of input multiplied by the joint probability between y and x. So we know this p of x is equal to 0.5, and this is the input given in the question. We just need to multiply these two things to get p of y. Since once we find p of y here, we have three different elements. They are, once we multiply this, we get this matrix. So it has three elements, that is py1, py2, and py3. So we get this answer, the second question. And then move on. So we have another relation, that is the joint probability between x and y is equal to the diagonal matrix multiplied by the conditional probability of output. So px1, the diagonal matrix is written here. So we'll substituting those values here. Diagonal matrix multiplied by the input matrix, channel matrix, that is given at the input, given in the question. Then when we multiply these two matrices, we should get pxy. And then when we multiply this row, this column, this is basically matrix multiplication. So when we multiply these two matrices, we get this. And from this matrix, we need to pick up some of the elements, that is x1, y1. What is x1, y1? That is 0.4. And we need to also pick x2, y1. What is that? That is x2, y1 is here. That is 0. So this is what is asked in the question. That is what we found here. So that is the end of this question. I mean, the solution. We got all the values that were asked in the question. So this is the end of today's lecture. Further, we have some references here. I mean, some ready references here. So this will be helpful for you. I mean, we have already discussed this, but some ready equations are given here. So that's the end of today's discussion.